Okay, back in it, talking about analysis. This is part 2 of analyzing themes in qualitative research. What is analysis? Well, analysis is when we search for patterns in data. And we search for patterns based on the codes that we developed. And we may have grouped this information so that it's nice and neat and clean, but it's the search for ideas that help explain why those patterns are there. So we see patterns that develop, and I mentioned in the previous lecture about keywords that are consistencies and repetition that just keeps popping up and popping up. And when we see those, where are they coming from? Why are they happening? Who's saying them? It's not enough to just take the initial, well, this is what we found. You need to dig deeper and figure out, okay, where did this come from? Why are they saying it? Is it a specific group? And we see patterns and make assumptions through word clouds all the time that we see on posters. We may see traffic. A great example is you're anticipating what's coming down the road, or that there's going to be a traffic delay. So you're anticipating or you're planning, I'm going to get off the interstate here and go around it. You have a dark alley and you have the option to walk a little bit further, and it's a lit alley. You're probably going to go towards the light as opposed to walk through the dark alley just because it's a little bit further. And again, you make those assumptions that it's going to be dangerous. You stand in a line and the line beside you is moving faster, and so you hop in that line. And every time you do that, what happens? It moves slower, and the line you were in starts moving. So we make assumptions based on what we're seeing happening. And if you've ever been to the airport, you see this all the time. And people do this, it's hilarious. How to avoid letting your own bias seep into your analysis? Well, one, you get some coding. Iterative reliability eliminates a lot of that, and we're going to talk about it. But you watch for disagreements between your informants. Watch for disagreements between what is happening, what you're seeing, what you're reading in the text. Watch for disagreements in your coders. Watch for when you feel the need to argue or defend something, that's a red flag that your bias is creeping into this information. Always check informant accuracy whenever you can. Anytime that you have negative evidence, that's a good thing. It's not always bad to get negative evidence, because we don't learn from getting things right all the time. It's very difficult, actually. If we do something and have success, it's very difficult to ever improve, because once we have something going that's working, we typically don't like to screw it up. But when in reality, when things are going well, sometimes you have to break it because there's a better way to do it. And so keep that in mind. Remember those things. Always look for alternative explanations and work your negative cases into your theory. When we're talking about your literature review, one of the things that I will consistently say is going to be, make sure that you find literature that works against your hypothesis. Who out there is trying to prove, or who out there has information that proves what you're saying is incorrect? Because we learn from that, folks. That is the key. We cannot always learn from getting it right all the time. In this program, everybody wants to make straight A's. Everybody gets real bent out of shape when they don't. But the reality is, when you get a question wrong, you go back and look it up, because you want to try to defend that I'm right, or that you're right and I'm wrong, and you want your point back. But if I were to go back and ask you that in your capstone defense about one question that you got wrong in the first year, you're probably going to know the answer, because, again, you learned that. It's burned into your mind now. Now, when we use modeling to analyze data, we have physical models. You think about playing with toy cars. You think about virtual models, playing video games. Numerical models, weather trends are a great example there, because they will use data that's collected from satellites, and they will build these models that visually we can see. But the honest truth is, those are not pictures from space. Those are models that are built. All of the when we look at them, is it going to snow? We look at the radar. Well, when you look from space, there's not green crawling across the earth. So again, weather maps are a perfect example of those visual models. And so here's an example. This is Graves and Lane all the way back in 1972. And this is going to be long, so I want you to just try to watch the screen, read it with me. There were 259 Navajo men were interviewed after they migrated to Denver, Colorado to live and work. And the intent was to determine the starting wages for these individuals. And they took about 3 years to figure this out. The starting wage This is the equation. And I'm not going to read through all of this right now, these abbreviations, because we're going to get to it. And it can be explained in a quantitative or a qualitative manner. So you look at this big, long algorithm to determine the starting wage. Well, from a quantitative side, and we've not really talked much about quantitative research, we'll get there, but it's more numbers driven, very objective. So you have a starting wage at 87 cents per hour. And remember, this was 1960. You add 10 cents for every year of education beyond the first 10, meaning that we hope that they will have, this individual had got to the 10th grade and they're going to keep going. You add 8 cents for having strong vocational training. So maybe they have been a blacksmith, maybe they have been a carpenter, who knows. 13 cents for each dollar earned in the best job prior to migration. So if they had a job working in a factory, something like that, 17 cents if the man is married, 11 cents if the man's father had worked for wages in the same career. Now, those last two things, why do you think that they asked that? Again, this is digging down into demographics. If they're married, they're more likely to stay at that job because their family will be there. If their father had worked in the same career, there's a great chance that the father would have passed on some skill and some knowledge to the son. Again, that equates to a more valuable employee. And so that's what all these abbreviations meant. Well, from a qualitative standpoint, we can look at it like this. What was the father's occupation? What's their marital status? What was their wages in their last job? What's their vocational training? What's their education? And when you look at the two different ways to kind of come about this, one is very heartless and cold, and the other one kind of lends itself to say, okay, well, there's a possibility. We can make a case, if they're married, they're going to stick around. And if their father worked in this business, it's the family business, they're passing it down. The kids probably worked, growing up working in the same vocation. If they've been in it for a long time and they're a really good welder or they're a really good carpenter, it's going to be very positive. If they were paid a lot of money in their last job, chances are they're good, they're worth the money, so we can do that as well. So again, you see how the two different views and how you speak about them, how it can be expressed. So let's look at a different problem. So a balloon first rose 200 meters from the ground, then moved 100 meters to the east, then dropped 100 meters. It then traveled 50 meters to the east and finally dropped straight on the ground. How far was the balloon from its original starting point? Now, many of you right now are having flashbacks to high school and studying for your SATs, but this is not a bad question, okay? Let's go back. So how would you do this? Well, you could draw a picture, and for me, personally, that's what I do. I would take a sheet of paper out, and I would draw a line up 200 meters, and then I would move east, and to me, in my mind, east is right, so I would draw to the right, and then I would drop 100 meters. So we're 100 meters off the ground. It then traveled 50 meters to the east. So now we've gone 150 meters to the right and finally dropped on the ground. How far was the balloon from its original starting point? Well, that whole up and down part doesn't matter. How far did they go to the east? They went 150 meters, right? So it depends on how you look at it. Some people would not draw a picture. They would just look at the numbers and immediately say, oh, this is what it is. Again, me personally, I'm very visual. I want to draw that line and move over. And then when I get to the end of the question, I'm going to say, oh, it didn't matter that they went up or down. Okay, example 2. At the grocery store, a bottle of olive oil costs 7 euros. That's about 2 euros more than at the supermarket. If you need to buy 7 bottles of olive oil, how much will it cost at the supermarket? So think about that one. Now, I'm not going to draw bottles of olive oil on this one because there's no direction in it. So if at the grocery store it costs 7 euros, it's 2 more at the supermarket, think about it. Think about it. Okay? When we identify those key concepts, we show linkages among the constructs or identify relationships so we can represent them visually. And again, my example with the balloon for me is drawing the line and moving around. Some of you may not have to do that. Some of you that may be looking at the olive oil question and wondering when I'm going to tell you the answer, you can figure that out, okay? test that the relationships hold for at least the majority of the cases being modeled. How do we know that that bottle of olive oil is about $2 more? Well, we take a lot of data collection. We take a lot of, hey, when you went to the store, how much was that bottle of olive oil? How much was that bottle of olive oil when you went to the store? And so we take all that in and we can figure out, it's about this. Think about gas. When gas was so high, you might drive across town. You may drive 10 miles to fill your car up and then drive back home to save 5 cents a gallon. And then you have to stop and think, am I really saving money by doing that? That's something to think about. When you identify key concepts, you're really just trimming down what you're doing. You have your coding. Look at my research question. How can I develop my codes to help answer my research question? Because there's a lot of things that you can code. There's a lot of things that you can try to find out of the material, but does it really matter? It's not important. It's just going to waste your time. Now, when you start to link these constructs, you group them into buckets, and you're going to hear me talk about buckets all the time. Always, always, always go back to the data. You have numerical matrices you can do, visual matrices. You can have a fish scale diagram. We're going to look at those. Flow charts, you've seen those forever. If this happens, then go here. If this happens, then go there. You have transition models, activity models. But once you get your model, you want to test it. Can the model be used in other cases? That's why you do pilot testing. That's why there's generalizations. That's why you do case studies. You guys are going to be exposed to case studies next winter. And we're going to talk about case studies because whatever you choose to do your research paper on, I would encourage you to write your case study on that because it's pretty much already going to be done. Now, we're going to stop there and let you kind of swirl around whether or not you should or shouldn't buy olive oil at the supermarket. And then we're going to talk about measurement. Okay, so again, if you need to take a break, and I will be back in just a moment with measurement.